Welcome back, ladies and gentlemen, to LeChatelier's principle. This is about manipulating the pressure of this equilibrium system. So let's say we have this ammonia reaction, and pressure can be changed by changing the volume of a container like that. This changes the pressure on every entity in the container, so the nitrogen, the hydrogen, and the ammonia. The rule here is an increase in pressure favors the side with fewer gas molecules. So if I decrease the volume of the container by squishing it down, that increases the pressure. Okay? When I increase the pressure, I favor the side with fewer gas molecules. So on my reactant side, I have one nitrogen and three hydrogens. Looking at the coefficients, it's 1 and 3. There's 4 molecules on the left, but only 2 ammonias on the right. So we favor the one with the fewer gas molecules, 2 ammonias. So that goes up, other side goes down. Now let's say we decrease the pressure. If I do this and I decrease the pressure, which means just lift up the syringe, I favor the side with more molecules. So the reactant side has 4, so that goes up, and this goes down. Okay, a couple of other things. When we add an inert gas, that will not shift equilibrium either way. Also, if I add a catalyst, that also does not shift equilibrium. It has no effect on equilibrium concentrations. Nothing happens. Speeds up the reaction, but the concentrations are the same. So how does temperature and pressure and concentration affect the value of Kc? Remember back in lesson 1, Kc equals products over reactants? Well, if I was to do the math on this equation right here, so I would take 0.156 squared divided by H2 and I2, the 0.0222, I would get a value of 49.4. Now look at the second one. The concentrations have all shifted, but when I do the math, I'm still getting 49.8. Might have some rounding errors in there. 49, 49, 49. Okay, the point is Kc is a constant, and when I manipulate concentration, that has no effect on Kc. Pressure has no effect on Kc. But if I manipulate temperature, I do change the value of Kc. Look at this. 300 degrees Celsius gives me a high Kc. 700 gives me a lower Kc. So temperature is the one variable that actually affects the value of Kc. Okay, now when we look at graphs, this is what these graphs look like. You can see in this graph where the equilibrium was disturbed or stressed. You can see on the green line, the moment we increased the concentration of N2O4, and then it shifted away, and NO2 went up, and N2O4 went down. Okay, you can see it right there. And then can you explain these graphs? So in the first one, it looks like the concentration of HF went up. That would be my stress. And then I shifted away. So CCl2F2, the blue line, goes up from there. HCl goes up. CClF goes down, which isn't shown on the graph, and HF goes down. Okay, what about B? Looks like we decreased the concentration of hydrochloric acid. That was our stress. We shift to replace it. So that goes up, down, down. All right, let's look at this one. What's going on in that graph? Well, it looks like SO2 is dropping, the orange line. The green line drops, and SO3 goes up. What would have caused that? What caused that to happen? Well, it looks like we've shifted to that side, and so that means it looks like to me here that our stress was we decreased the temperature, and that caused the shift to products. Okay, final one. Look at this graph. Now, notice the sharp vertical change on every entity, SO2, O2, and SO3. The concentrations all changed. which to me suggests that we've had a pressure change. In other words, the shape of the container changed. Maybe if it was a 1 liter container, so let's just use a simple example. Everything was 1 mole per liter. Now the container changes, like pushing the syringe down, and it's now like a 250 milliliter container. The concentrations just went way up because it's not per liter, it's per 250 mils now. Okay, so what happened here? It looks like SO2 went down, O2 went down, and SO3 went up. What shift, what pressure change would have caused that? Well, there's 3 moles on the reactant side and 2 moles on the product side. What shifts to the fewer moles? We increase the pressure, and that favors the side with the fewest moles. Okay, so that was our stress. All right, ladies and gentlemen, that is it for LeChatelier's principle, the end. Thank you for watching.